What if something invisible, heavier than 10 suns, suddenly entered our solar system? No explosion, no warning, just gravity, quietly rewriting every orbit. Most people picture a black hole as a cosmic vacuum cleaner, a dark, hungry mouth that sucks in everything around it. That image is wrong. A black hole doesn't need to swallow anything to destroy everything. The real danger was never consumption. It was disruption. Gravitational disruption so subtle, so slow, and so catastrophic that by the time you noticed something was wrong, the solar system you knew would already be gone. Tonight, you're going to find out exactly how a rogue black hole could wander into our solar system. What sizes are plausible, what paths are likely, and why the answer reveals something unsettling about how fragile the architecture of our cosmic neighborhood really is. Before we dive in, if you love exploring gravitational mysteries as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. I read every comment. Now, let's begin. To understand what a rogue black hole would actually do to our solar system, we first need to understand what our solar system actually is. Not in the poetic sense, not as a diagram in a textbook, but as a mechanical system, a gravitational machine. Because when you strip away the beauty, that's what it is. It's a set of masses bound together by gravity, each one orbiting the sun along a path that's been refined over billions of years through a process that was anything but gentle. The solar system we see today, 8 planets in relatively circular orbits, all roughly in the same plane, with stable asteroid belts and predictable cometary reservoirs, is not the solar system that formed. It's the solar system that survived. 4.5 billion years ago, the solar nebula collapsed. Dust became pebbles, pebbles became planetesimals, planetesimals became protoplanets, and protoplanets began a violent, chaotic competition for dominance. There were almost certainly more planets than the 8 we have now. Simulations suggest there may have been dozens of Mars-sized bodies in the early inner solar system alone, crashing into each other, merging, fragmenting, and, crucially, gravitationally scattering each other into new orbits. Some were flung into the sun. Some were ejected from the solar system entirely, becoming rogue planets wandering the galaxy with no star to call home. And the ones that remained, Mercury, Venus, Earth, Mars, are the survivors. Not because they were the biggest or the strongest, but because they happened to end up in orbits that didn't intersect with anything else massive enough to destabilize them. This is the first thing to understand. The solar system is stable, but it's not robustly stable. It's what physicists call marginally stable, meaning it works perfectly under current conditions, but it's not designed to absorb large perturbations. There's no deep structural reason why 8 planets must orbit in their current configuration. There's no law that says Earth must be at 1 astronomical unit from the Sun, or that Jupiter must be at 5.2. These are outcomes of history, contingent, path-dependent, and sensitive to initial conditions. Here's an analogy that captures reality. Imagine a set of ball bearings rolling in grooves on a slightly tilted table. Each groove is shallow, just deep enough to keep the ball bearing on track as long as nothing disturbs it. A gentle breeze, a small vibration. The bearings stay in their grooves. But tilt the table a little more, or give it a sharp knock, and the bearings start jumping grooves, colliding with each other, rolling off the edge. The grooves themselves haven't changed. The physics hasn't changed. What changed was the introduction of energy, external energy, that exceeded the system's ability to absorb it. A rogue black hole entering our solar system would be that knock on the table. But before we start modeling what happens when such an intruder arrives, we need to answer a more basic question. How likely is this scenario in the first place? Is this pure science fiction, or is there a genuine, calculable probability that a black hole could wander into our neighborhood? The answer is more nuanced than you might expect. Our galaxy, the Milky Way, contains somewhere between 100 million and 1 billion stellar mass black holes. These are black holes formed from the collapse of massive stars, typically ranging from about 5 to perhaps 50 solar masses. That number, 100 million to 1 billion, sounds enormous, and it is. But the Milky Way is also enormous. Its disk is roughly 100,000 light-years across, and the volume it occupies is staggering. So even with hundreds of millions of black holes scattered throughout the galaxy, the average distance between any two of them is measured in light-years. The nearest known black hole to Earth, as of recent surveys, is a system called Gaia BH1, located about 1,500 light-years away in the constellation Ophiuchus. It's a stellar mass black hole, roughly 10 times the mass of the Sun, orbiting a Sun-like companion star. 1,500 light-years is, by astronomical standards, practically next door. But by human standards, it's an incomprehensible distance. Light itself takes 15 centuries to cover it. A spacecraft traveling at the speed of the Voyager probes, about 17 kilometers per second, would take roughly 26 million years to get there. So the nearest known black hole is safely distant. But here's where it gets interesting. Most stellar mass black holes are invisible. They don't emit light. They don't glow. Unless they're actively consuming matter, pulling gas from a companion star, generating an accretion disk, producing X-rays, they are functionally undetectable by conventional telescopy. A solitary black hole drifting through interstellar space, not feeding on anything, is one of the most difficult objects in the universe to detect. And that means the actual nearest black hole could be far closer than 1,500 light-years. It could be 100 light-years away. It could, in principle, be 10 light-years away, and we simply wouldn't know. This isn't speculation. It's a statistical consequence of the numbers. If the Milky Way contains, conservatively, 200 million stellar mass black holes, and those black holes are distributed throughout the galactic disk with some concentration toward the center, then the average density of black holes in our local neighborhood of the galaxy works out to something like 1 black hole per every few hundred cubic light-years. That means within a sphere of, say, 50 light-years centered on our Sun, a sphere that contains roughly 2,000 stars. There could be, statistically, anywhere from 0 to a handful of stellar mass black holes drifting silently through the dark. None of them are likely to be on a collision course with us. The odds of a direct encounter, a black hole passing through the inner solar system within the orbit of Neptune, are vanishingly small over any human timescale. Various estimates put the probability at roughly once every 100 billion to 1 trillion years. Given that the universe is only 13.8 billion years old, and the Sun will only last another 5 billion, this means statistically it almost certainly won't happen before our Sun dies. Almost certainly. But almost certainly is not never. And in astronomy, low probability events that have enormous consequences occupy a special category of concern. They may not be worth worrying about on any practical timescale, but they are profoundly worth thinking about, because they reveal the hidden fragility of systems we assume are permanent. And besides, the physics of what would happen is extraordinary, regardless of likelihood. So let's do this properly. Let's introduce a rogue black hole into our solar system and trace exactly what happens, step by step, based on the best physics and computational models we have. First, we need to define the intruder. Not all black holes are created equal, and the mass of the incoming object is, along with its trajectory and velocity, the single most important variable in determining the outcome. Stellar mass black holes, the kind formed from collapsed massive stars, typically range from about 5 solar masses to around 50 solar masses, though mergers detected by gravitational wave observatories like LIGO have revealed black holes up to nearly 100 solar masses. For our purposes, let's consider a reasonably common scenario: a black hole of 10 solar masses. This is a well-characterized mass, consistent with numerous observations, and it represents the kind of object most likely to be drifting through interstellar space as a rogue. 10 solar masses. That means this object has 10 times the gravitational pull of our Sun at any given distance. From far away, it behaves just like any other 10 solar mass object. A massive star, a compact neutron star, anything. Gravity doesn't care about density or composition. It cares about mass and distance, full stop. The black hole's event horizon, the boundary beyond which nothing can escape, is only about 30 kilometers in radius for a 10 solar mass black hole. 30 kilometers. You could fit it comfortably inside a mid-sized city. But its gravitational reach extends vastly farther than that, because gravity has infinite range. At a distance of 1 astronomical unit, the Earth-Sun distance, this black hole would exert 10 times the gravitational force that our Sun does. That last point is critical. The event horizon is irrelevant for what we're about to discuss. Nobody is falling into the black hole. No planet gets swallowed. The event horizon is a tiny, tiny target, and orbital mechanics essentially guarantees that objects will swing past it rather than plunge into it, just as comets swing past the Sun rather than hitting it directly. The danger is not the event horizon. The danger is the gravity. Ordinary, Newtonian, inversely proportional to distance squared gravity, and what it does to orbits that have been stable for eons. Now, let's talk about velocity, because this matters enormously. A rogue black hole drifting through the galaxy would have a velocity relative to our Sun, determined by the general kinematics of stellar motion in the galactic disk. Stars and rogue compact objects in our neighborhood typically move relative to each other at speeds of around 20 to 50 kilometers per second. Some move faster, some slower, depending on their galactic orbits. But 20 to 50 kilometers per second is a reasonable range for the approach speed of a rogue black hole. To put that in perspective, Earth orbits the Sun at about 30 kilometers per second. So, a rogue black hole might be traveling at roughly the same speed as Earth's orbital velocity, give or take. This is important because it tells us something about the encounter timescale. A body moving at, say, 30 kilometers per second, passing through the inner solar system, crossing a region roughly 10 astronomical units across, the distance from the Sun to Saturn, would take approximately 200 days to traverse that space, just over half a year. That's not instantaneous. It's not a bullet whipping through in seconds. It's a slow, grinding passage, during which every planet feels the intruder's gravity pulling on it, gently at first, then more strongly as the black hole approaches, then fading as it recedes. And this extended timescale makes everything worse. If the encounter were truly instantaneous, a gravitational impulse lasting only seconds or minutes, the planets wouldn't have time to respond. Their orbits would barely change. It's precisely because the encounter lasts months that the gravitational perturbations can accumulate, compound, and cascade into permanent orbital changes. Here's an analogy from everyday experience. If you push a child on a swing with a single sharp shove, the swing moves a little. But if you apply a gentle, sustained push that's timed to the swing's natural frequency, you can build the amplitude enormously over many cycles. This is resonance. And while a single pass of a rogue black hole isn't exactly resonance, the principle of sustained perturbation applies. The longer the gravitational influence acts, the more it can alter trajectories. Now we have our setup. A 10 solar mass black hole enters our solar system from interstellar space, traveling at roughly 30 kilometers per second relative to the Sun. The question is, what path does it take, and what does it encounter along the way? Here's where the geometry becomes critical. The solar system is not a uniform sphere of planets. It's a thin disk. The 8 major planets orbit within a few degrees of a common plane, the ecliptic, and most of them are concentrated in specific distance ranges. The inner solar system, Mercury, Venus, Earth, Mars, occupies the region from about 0.4 to 1.5 astronomical units from the Sun. The asteroid belt stretches from roughly 2 to 3.5 astronomical units. The gas giants, Jupiter and Saturn, sit at 5.2 and 9.5 astronomical units respectively. And the ice giants, Uranus and Neptune, are at 19.2 and 30 astronomical units. A rogue black hole approaching from a random direction in 3-dimensional space could enter the system at any angle. It could come in along the ecliptic plane, passing through the disk of planets like a bowling ball through pins. Or it could come in at a steep angle, plunging through the plane from above or below, interacting most strongly with whatever planets happen to be nearest its path at that moment. The angle of approach profoundly affects which planets are most perturbed and in what order. But regardless of the approach angle, one thing is universally true. The rogue black hole's gravity will interact most strongly with whatever mass is closest to its trajectory, and the strength of that interaction falls off with the square of the distance. Double the distance, quarter the gravitational effect. Triple the distance, 1/9 the effect. This means the encounter is fundamentally local. The black hole doesn't uniformly disturb the whole solar system at once. It creates a corridor of strong perturbation along its path, and planets outside that corridor may barely feel it at first. First, that qualifier is essential, and we'll return to it. Let's begin tracing the encounter from the outside in. Long before the rogue black hole reaches the inner solar system, it will pass through the outermost regions of our Sun's gravitational domain, the Oort Cloud. The Oort Cloud is a theoretical, but well-supported, shell of icy bodies surrounding the Sun, at distances ranging from about 2,000 to 100,000 astronomical units. That outer boundary, 100,000 astronomical units, is roughly 1.6 light-years from the Sun, nearly half the distance to the nearest star, Proxima Centauri. The Oort Cloud is thought to contain trillions of icy objects, ranging from pebble-sized to perhaps tens of kilometers across, with a combined mass of perhaps 5 to 100 Earth masses. These are the remnants of the original solar nebula, objects that were gravitationally scattered outward by the giant planets during the solar system's chaotic youth and now orbit the Sun in vast, lazy, nearly circular paths that take millions of years to complete. A rogue black hole approaching from interstellar space would enter the Oort Cloud long before it reached the planets. And its gravitational influence on these loosely bound objects would be significant. Remember, the objects in the Oort Cloud are only weakly bound to the Sun. They orbit at such vast distances that the Sun's gravitational hold on them is tenuous. A passing massive object can easily strip them away, flinging them into interstellar space, or, more worryingly, deflecting them inward toward the inner solar system. This is not a hypothetical mechanism. It's the same process that's believed to send long-period comets raining into the inner solar system today. Passing stars, molecular clouds, and galactic tidal forces periodically disturb the Oort Cloud, nudging objects onto new orbits that bring them close to the Sun. A close stellar passage, a star passing within 1 or 2 light-years of the Sun, is thought to cause a noticeable increase in the flux of long-period comets, with a delay of 1 million years or so as the deflected objects slowly fall inward. A 10 solar mass black hole would be far more disruptive than a passing star of 1 solar mass. Its gravitational reach, the sphere within which its pull exceeds the Sun's hold on Oort Cloud objects, would be correspondingly larger. Trillions of icy bodies would have their orbits altered. Some would be ejected from the solar system entirely. Others would be flung inward on orbits that would, over the following millions of years, bring them through the inner solar system. The result would be a comet shower, a sustained increase in the rate of comets entering the inner solar system, lasting perhaps 10 to 20 million years. And comet showers are not trivial. One of the leading hypotheses for periodic mass extinction events on Earth involves comet showers triggered by gravitational disturbances of the Oort Cloud. A surge in the number of comets passing through the inner solar system means a surge in the probability of large impacts on Earth. The asteroid that killed the non-avian dinosaurs 66 million years ago was roughly 10 to 15 kilometers across. A comet of similar size, arriving at higher velocity, would be equally devastating. And during a comet shower, the probability of such an impact could increase by a factor of 10 or more over background rates. But the comet shower would be a delayed consequence, something that unfolds over millions of years after the black hole has already passed through. The immediate effects would be far more dramatic. As the rogue black hole crosses the threshold of the Kuiper Belt, the region of icy bodies extending from about 30 to 50 astronomical units, home to Pluto and its cohort of dwarf planets, it begins to interact gravitationally with objects that, while still relatively weakly bound to the Sun, are far closer and more dynamically important than the Oort Cloud population. Kuiper Belt objects have orbital periods of hundreds of years, not millions. A significant perturbation to the Kuiper Belt could scatter objects inward on timescales of centuries, not millennia. But the Kuiper Belt, while interesting, is not where the real stakes lie. The real stakes lie with the giant planets. And here is where we need to talk about Jupiter, because Jupiter is, in many ways, the keystone of the solar system's architecture. Jupiter is massive. At 318 times the mass of Earth, it contains more mass than all the other planets combined, twice over. Its gravitational influence shapes the orbits of asteroids, guides the trajectories of comets, maintains the gaps in the asteroid belt through orbital resonances, and, most critically, helps stabilize the orbits of the inner planets. Jupiter is not just a planet. It's a gravitational anchor. And what happens to Jupiter during the encounter with a rogue black hole is arguably the most important single variable in determining the fate of the solar system. Here's where it gets strange. If the rogue black hole's trajectory brings it within a few astronomical units of Jupiter, close enough for the gravitational interaction to be comparable to or stronger than the Sun's pull on Jupiter at that distance, then Jupiter's orbit will change. The magnitude and direction of the change depend on the geometry, how close the black hole passes, at what angle, and at what relative velocity. But in general, a close encounter with a 10 solar mass object would impart a significant velocity change to Jupiter. Computational simulations of such encounters suggest a range of possible outcomes depending on the exact initial conditions. In some scenarios, Jupiter's orbit becomes more elliptical. Its eccentricity, a measure of how elongated its orbit is compared to a perfect circle, increases from its current value of about 0.048, which is nearly circular, to values of 0.2, 0.3, or even higher. A Jupiter with an eccentricity of 0.3 would swing between roughly 3.6 astronomical units from the Sun at closest approach and 6.8 astronomical units at farthest. Currently, it oscillates between only 4.95 and 5.46. That change might sound modest in absolute terms, but it would be gravitationally catastrophic for the rest of the solar system. In other scenarios, Jupiter is ejected entirely, flung out of the solar system on a hyperbolic trajectory, never to return. This is the outcome when the energy imparted by the black hole's gravitational interaction exceeds Jupiter's binding energy to the Sun. For a 10 solar mass intruder passing within about 1 to 2 astronomical units of Jupiter at typical interstellar velocities, ejection is a plausible outcome. And in still other scenarios, Jupiter is captured into a new orbit, perhaps a much wider orbit, perhaps a highly eccentric orbit that takes it far from the Sun and then brings it crashing back through the inner solar system. Each of these outcomes has profoundly different consequences for Earth and the other planets, but they all share one thing in common. They destroy the stability that the solar system has maintained for billions of years. Now here's the part that makes this so much worse than a simple Jupiter move story. Jupiter doesn't exist in isolation. It exists in a web of gravitational relationships with every other body in the solar system. And the most important of these relationships is its interaction with Saturn. Jupiter and Saturn are in a near resonance with each other. Jupiter's orbital period is about 11.9 years. Saturn's is about 29.5 years. That's close to a 5-to-2 ratio. For every 5 orbits Jupiter completes, Saturn completes approximately 2. This near resonance means the two planets gravitationally tug on each other in a pattern that repeats roughly every 60 years. Over billions of years, this interaction has shaped both planets' orbits and helped maintain the stability of the outer solar system. If Jupiter's orbit changes significantly, becomes more eccentric, shifts inward or outward, or tilts relative to the ecliptic, its resonance with Saturn is disrupted. And when that resonance is disrupted, Saturn's orbit changes too. Not because the black hole directly perturbed Saturn, but because Saturn's orbital stability depended on Jupiter's orbit being approximately where it was. This is the cascade. Jupiter's perturbation propagates to Saturn. Saturn's perturbation propagates to Uranus and Neptune. And eventually, the effects ripple inward, to the asteroid belt, to Mars, to Earth. This cascade doesn't happen instantaneously. It unfolds over thousands, hundreds of thousands, even millions of years. The timescale depends on the magnitude of the initial perturbation and the specifics of the new orbital configurations. But the direction is clear and consistent toward instability, toward chaos. And here, when we say chaos, we're not using the word loosely. We're using it in the precise mathematical sense of chaos theory. Sensitive dependence on initial conditions. The solar system's orbital dynamics, even in its current undisturbed state, are formally chaotic on timescales longer than about 10 million years. This was demonstrated in landmark numerical simulations by Jacques Lascar in the late 1980s and early 1990s. Lascar showed that tiny uncertainties in the current positions and velocities of the planets, uncertainties smaller than our ability to measure, grow exponentially over time, making the detailed configuration of the solar system fundamentally unpredictable more than about 50 to 100 million years into the future. What this means is that the solar system is not like a clock, not a machine that, once set in motion, ticks along the same path forever. It's more like a ball balanced on a hilltop. Right now, the ball is nearly stationary, held in place by the gentle curves of the terrain. But give it a nudge, even a small one, and it begins to roll. And once it starts rolling, you cannot predict which valley it will end up in. A rogue black hole passing through the solar system would be far more than a small nudge. It would be a violent shove. And the hill the ball is balanced on, our finely tuned orbital architecture, is not as smooth and gentle as we might hope. Let's trace the specifics of what happens to the inner solar system, because this is where things become personal. Suppose Jupiter's orbit becomes significantly eccentric after the encounter, say an eccentricity of 0.2 or higher. Jupiter now swings much closer to the Sun than it used to. On each orbit, it passes through the asteroid belt with more gravitational authority and at closer range than before. The asteroid belt, which is currently maintained in a state of relative order by the balance of gravitational influences from Jupiter and the Sun, begins to destabilize. Asteroids in the belt occupy specific zones of stability, regions between the major Kirkwood gaps, which are caused by orbital resonances with Jupiter. These gaps are well defined, well studied, and have been stable for billions of years. But they depend on Jupiter being where it is, moving how it moves. Change Jupiter's orbit, and the resonance structure of the asteroid belt changes with it. Gaps shift. Formerly stable zones become unstable. Asteroids that have orbited peacefully for 4 billion years are suddenly on chaotic trajectories, and some of those trajectories cross the orbits of Mars, Earth, Venus, and Mercury. The result is an increase, potentially a dramatic increase, in the rate of asteroid impacts on the inner planets. Not immediately, not in years or decades, but over hundreds of thousands to millions of years, the inner solar system would experience a bombardment event. A new period of heavy impacts, reminiscent of the late heavy bombardment that the inner solar system may have experienced about 4 billion years ago, when gravitational reshuffling of the giant planets, possibly triggered by a resonance crossing between Jupiter and Saturn, scattered asteroids and comets inward. This sounds like it solves the problem, or at least contains it. The planets themselves stay in orbit, and the damage is limited to an increased impact rate. Wear a hard hat for a few million years, geologically speaking, and wait it out. That's the optimistic interpretation. But it doesn't hold up, because the perturbation to Jupiter doesn't just affect the asteroid belt, it affects Mars. Mars orbits at 1.52 astronomical units from the Sun. A Jupiter with increased eccentricity passes closer to Mars on each orbit, and the gravitational perturbation to Mars's orbit accumulates over time. Mars's own eccentricity increases. Its orbit begins to shift. And Mars's orbit, it turns out, is coupled to Earth's. This is one of the most profound and unsettling results from Lascar's simulations. In the current solar system, without any external perturbation, there exists a small but non-zero probability that Mars's orbit could become so eccentric over the next several billion years that it collides with Earth. The probability is estimated at roughly 1 to 2% over the remaining lifetime of the Sun. That probability is already uncomfortable. But it depends on the solar system remaining in approximately its current configuration. Introduce a significant perturbation to Jupiter, and thereby to Mars, and that probability doesn't increase incrementally. It can jump dramatically. In some simulated scenarios where Jupiter's eccentricity is artificially increased, the inner solar system becomes unstable on timescales as short as a few million years. Mars is ejected from the solar system, or it collides with Earth, or it collides with Venus. Mercury, the smallest and most weakly bound of the inner planets, is often the first to go, flung into the Sun, or ejected into a crossing orbit with Venus. And once one inner planet is displaced, the remaining ones are no longer in a stable configuration. They're in a new dynamical state that has never been explored, a state with no guarantee of stability, because the stability of the original configuration depended on all the players being present and in their designated roles. This is the cascade in full. A rogue black hole enters the solar system. It directly perturbs Jupiter. Jupiter's changed orbit destabilizes Saturn. The outer solar system restructures. The asteroid belt loses its stability. Mars begins to wander, and Earth, our Earth, is no longer in a safe orbit. But here's the problem with everything said so far. We've been discussing a relatively specific scenario, a 10 solar mass black hole passing through the outer solar system, close enough to significantly perturb Jupiter, but not passing through the inner solar system itself. This is, in some sense, the gentle version. The version where the black hole doesn't come anywhere near Earth, doesn't interact directly with any inner planet, and still manages to dismantle the entire system through cascading gravitational effects. The gentle version still destroys us. It just takes longer. Now let's talk about what happens if the black hole passes through the inner solar system. If a 10 solar mass black hole passes within 1 astronomical unit of the Sun, within Earth's orbital radius, the gravitational effects are immediate, dramatic, and in many cases, irreversible on timescales of days to months. At equal distance, a 10 solar mass black hole would exert 10 times the Sun's gravitational pull. But in reality, the forces Earth experiences depend on its changing distance from both objects during the encounter. Any planet caught on the same side of the Sun as the black hole during closest approach would experience a tidal tug that could radically alter its orbit in a single pass. Here's what the simulations show, and these are real simulations, N-body gravitational integrations, run by researchers at institutions including the University of Cambridge, the Institute for Advanced Study in Princeton, and multiple groups in Japan and Europe. The outcomes depend sensitively on the exact geometry, but some patterns emerge consistently. Earth, if it happens to be on the same side of the Sun as the black hole during closest approach, can be flung into a radically different orbit. In some runs, Earth ends up on a highly eccentric orbit that takes it much closer to the Sun at perihelion, perhaps to the orbit of Venus or even Mercury, and much farther at aphelion, perhaps to the orbit of Mars or beyond. The consequences for Earth's climate would be catastrophic. At perihelion, Earth would receive 4 or more times its current solar radiation, driving surface temperatures above the boiling point of water across much of the planet. At aphelion, it would receive a fraction of its current radiation, plunging into deep freeze. The oceans would cycle between boiling and freezing on a timescale of months. No complex life could survive. In other runs, Earth is ejected from the solar system entirely, flung into interstellar space as a rogue planet, carrying its moon along, drifting through the galaxy without a star. We'll return to that scenario later, because it raises questions that go beyond physics into something more fundamental. In still other runs, Earth is captured into a tighter orbit around the Sun, closer than its current 1 astronomical unit. Or it's shifted outward to 2 or 3 astronomical units. Or its orbital plane is tilted dramatically relative to its current orientation. Each of these outcomes produces a different long-term fate, but none of them resemble the Earth we know. And Earth might not be the planet most dramatically affected. Mercury, being the closest planet to the Sun and the least massive, is extraordinarily vulnerable to gravitational perturbation. In many simulations, Mercury is the first planet to be lost, ejected from the solar system, thrown into the Sun, or deflected into a crossing orbit with Venus, leading to a collision that would produce an entirely new body. Venus, which is similar in mass and size to Earth, is more resilient but still highly susceptible to orbital changes during a close encounter. Mars, being relatively small and orbiting in the gap between the inner planets and Jupiter, is also highly vulnerable. In scenarios where the black hole passes through the inner solar system, Mars is frequently ejected entirely. But here's the truly disturbing part. Even if Earth, by some extraordinary coincidence of timing and geometry, emerges from the encounter with a relatively unchanged orbit, even if the black hole passes through and Earth happens to be on the opposite side of the Sun, maximally distant from the intruder, the solar system Earth exists in is no longer the same solar system. The other planets have been rearranged. Jupiter may be gone or on a new orbit. Saturn may be wildly eccentric. The asteroid belt may be in chaos. And in this new, destabilized configuration, Earth's orbit, even if initially unchanged, is no longer guaranteed to remain stable. The gravitational guardrails that kept Earth safe for 4.5 billion years have been removed. And on timescales of millions of years, the absence of those guardrails will make itself felt. This is perhaps the deepest lesson of the entire scenario. The direct effects of the black hole's passage, while dramatic, are almost secondary to the indirect effects. The real destruction is architectural. The solar system is a structure, a gravitational architecture. And like any structure, its components depend on each other for stability. Remove one load-bearing wall, and the roof doesn't collapse immediately, but it begins to sag, and eventually it falls. Now, let's talk about the Sun itself, because the Sun is not immune to this encounter, and its response adds another layer of consequence. If the rogue black hole passes close to the Sun, within a few astronomical units, the Sun's position changes, not dramatically. The Sun is massive, 1 solar mass, obviously, and the black hole is 10 solar masses. So the gravitational interaction between them is essentially the interaction between a 1 solar mass body and a 10 solar mass body. The Sun will be deflected from its current position. It will acquire a velocity change, a kick, proportional to the mass of the black hole, the closeness of the approach, and the duration of the interaction. For a 10 solar mass black hole passing at 1 astronomical unit from the Sun at 30 kilometers per second, the velocity kick imparted to the Sun would be on the order of a few kilometers per second. That might not sound like much, but the Sun's current velocity through the galaxy is about 220 kilometers per second, and its velocity relative to nearby stars is roughly 20 to 30 kilometers per second. A kick of a few kilometers per second changes the Sun's trajectory through the galaxy. It shifts the Sun's orbit within the Milky Way, which changes the environments the solar system will pass through over the coming hundreds of millions of years. Different stellar densities, different molecular cloud encounters, different cosmic ray environments. But more immediately, the kick also changes the Sun's position relative to its own planets. The Sun and its planets orbit a common center of mass, the barycenter, and any sudden displacement of the Sun shifts the barycenter, which means every planetary orbit adjusts slightly. For the outer planets, which orbit slowly, this is a minor perturbation. For the inner planets, which orbit quickly and are more tightly bound, the effect is more pronounced. It's yet another destabilizing input in a system already being hammered by the black hole's direct gravitational influence. There's one more effect on the Sun worth mentioning: tidal interaction. As the black hole passes near the Sun, it raises tides on the Sun's surface, the same way the Moon raises tides on Earth's oceans, but on a far more violent scale. The Sun is a ball of plasma, not a rigid body, and tidal forces from a 10 solar mass object at close range could potentially induce oscillations, surface disturbances, or even mass loss, though the latter would require an extremely close passage, probably within a few solar radii, which would place the black hole inside the Sun's outer atmosphere. At that range, the encounter becomes even more exotic. The black hole would pass through the Sun's corona, or even through the Sun itself, and the interaction would involve not just gravity, but hydrodynamics, radiation, and magnetic fields. The black hole wouldn't consume the Sun. It would pass through too quickly for significant accretion. But the gravitational disruption of the Sun's interior could trigger a massive flare event, ejecting solar material at high velocity and potentially triggering massive surface disturbances or flares, though the Sun's core fusion processes would likely remain largely unaffected. This is entering the realm of the speculative, because no one has observed such an event, and the computational modeling of a compact object transiting through a stellar interior is extraordinarily complex. But the theoretical possibility exists, and it adds yet another dimension of danger to an already catastrophic scenario. Let's shift our attention now to something that might seem secondary, but is actually central to the human experience of this event. What would it look like? What would we see, feel, and measure in the years, months, and days before and during the encounter? This is where physics becomes personal, because one of the most unsettling aspects of a rogue black hole encounter is how invisible it would be until it was far too late to do anything about it. A 10 solar mass black hole is only 30 kilometers across at its event horizon. That's smaller than a city. It emits no light, no radiation, nothing, unless it's actively accreting matter. A solitary rogue black hole drifting through interstellar space would be, for all practical purposes, invisible. No telescope could see it directly. We wouldn't know it was coming. But wait, couldn't we detect it indirectly? Through gravitational lensing, perhaps? In principle, yes. A massive object warps space-time, and light from background stars passing near it is bent, creating a characteristic brightening and distortion called gravitational microlensing. This is a real effect, and it's been used to detect compact objects, including potential isolated black holes, by surveys like OGLE and MOA, which monitor millions of stars simultaneously and look for the telltale brightening signature. But here's the limitation. Microlensing events are rare, brief, and require the compact object to pass almost exactly between us and a background star. The probability of detecting any particular rogue black hole via microlensing is extraordinarily low unless you're conducting a massive continuous survey of millions of stars. And even then, you'd detect the lensing event while it was happening, or after it had peaked. By the time you confirmed that the lens was a 10 solar mass object and calculated its trajectory, it might already be entering the Oort Cloud. There would also be astrometric signatures, tiny shifts in the apparent positions of stars as the black hole's gravity deflected their light. The Gaia Space Telescope, which measures the positions of over 1 billion stars with extraordinary precision, could in principle detect the astrometric wobble caused by a nearby massive object. But the effect is subtle, and disentangling it from other astrometric signals, stellar proper motion, parallax, binary orbital motion, is a formidable data analysis challenge. It's plausible that Gaia data, carefully analyzed, could reveal the presence of nearby dark massive objects. But we don't yet have algorithms sophisticated enough to do this routinely. The bottom line is this. With current technology, we would likely have little to no warning of a rogue black hole's approach. We might detect anomalous perturbations of Oort Cloud objects, or Kuiper belt objects years before the encounter. Subtle shifts in the orbits of distant icy bodies that couldn't be explained by known gravitational influences. We might notice a strange pattern of microlensing events in a particular direction of the sky. But translating these subtle signals into a definitive detection, there is a 10 solar mass black hole heading toward us at 30 kilometers per second, arrival in 50 years, would require both extraordinary luck and extraordinary analytical capability. And even if we detected it, there would be nothing we could do. No technology exists or is plausible on any foreseeable timescale that could deflect a 10 solar mass object. We struggle to contemplate deflecting a 1-kilometer asteroid. A black hole with the mass of 10 suns is beyond any conceivable intervention. We would simply watch it come. The year is 2025, and we are blissfully unaware of an object approaching from the direction of the constellation Lyra at 28 kilometers per second. It is still 400 astronomical units away, 10 times the distance to Pluto, and will reach the inner solar system in approximately 20 years. It has no accretion disk, no companion star, no emissions of any kind. It is a gravitational ghost, 10 times the mass of the Sun, invisible against the blackness of space. The only evidence of its existence is a pattern of perturbations in the orbits of half a dozen trans-Neptunian objects, perturbations so small that they are buried in the noise of current survey data. No one has noticed them. No one will, for at least another decade. The first sign that something is wrong comes in the early 2030s, when a routine update to the ephemeris of Neptune, the precisely calculated table of its predicted position over time, reveals a discrepancy. Neptune is not quite where it should be. The discrepancy is tiny, a fraction of an arcsecond, but it's real and it's growing. Astronomers initially attribute it to modeling errors or to the gravitational influence of an undiscovered large trans-Neptunian object, a hypothesis that has been floated for decades. Papers are published, theories are proposed. A search is initiated for the hypothetical object. They are looking for the wrong thing. They are looking for a planet. By the mid-2030s, the perturbation has grown, and Uranus is now showing anomalies as well. Jupiter and Saturn's positions are subtly off their predicted ephemerides. The pattern is consistent with a massive object approaching from beyond Neptune on a specific trajectory. Gravitational modeling narrows the possibilities. The mass is too high for a planet, at least several solar masses. A star would be visible. The only remaining explanation is a compact object, a neutron star or a black hole. The astronomical community reacts with a mixture of fascination and alarm. Dedicated searches using gravitational microlensing and astrometry are initiated, and within 2 years, the object is confirmed. It is real. It is a black hole. Its mass is estimated at 9.7 solar masses, plus or minus 1.2. Its trajectory will bring it within approximately 3 astronomical units of the Sun. It will pass through the solar system in the early 2040s. And there is nothing anyone can do. This imagined scenario is, of course, fictional, but every element of it is physically plausible. The detection timeline, the observational signatures, the mass estimate, all of it is consistent with our current understanding of both rogue black holes and our observational capabilities. The scenario is designed to illustrate a point. The gap between detection and response is, for this class of threat, effectively infinite. We could know it was coming and still be powerless to stop it. But awareness has value, even without the ability to act. So let's continue. Let's trace what happens as the black hole reaches the planetary region. By the time the black hole crosses Neptune's orbit, roughly 30 astronomical units from the Sun, it has been gravitationally interacting with the outer solar system for years. Neptune, Uranus, and their extensive moon systems have been perturbed. The Kuiper belt is in disarray, with objects scattered in all directions. But the effects on the inner solar system are still negligible. The black hole is too far away, and its gravitational influence on bodies close to the Sun is swamped by the Sun's own gravity. This changes as the black hole passes Saturn's orbit at 9.5 astronomical units. Now the gravitational tug on Jupiter, the most massive planet, the one whose stability matters most, becomes significant. Jupiter feels a pull from the black hole that is, at closest approach, comparable to the Sun's pull. Its orbit begins to visibly shift. And because Jupiter's orbital period is about 12 years, even a few months of strong perturbation can impart a meaningful velocity change. The black hole continues inward. It passes Jupiter's orbit at 5.2 astronomical units. If the geometry is favorable, if Jupiter happens to be on the same side of the Sun as the black hole during this passage, the interaction is severe. Jupiter's velocity could change noticeably, potentially altering its orbit depending on the exact geometry of the encounter. That doesn't sound like much, but Jupiter's orbital velocity is only about 13 kilometers per second. So a change of even half a kilometer per second represents a nearly 4% alteration. This is enough to significantly change Jupiter's eccentricity and potentially its semi-major axis. The black hole passes through the asteroid belt. Asteroids are flung in all directions. Some are accelerated to escape velocity and leave the solar system. Others are deflected inward toward the inner planets. The gravitational focusing effect of the black hole creates a cone of disturbed trajectories behind it, a wake of displaced objects. And then the black hole enters the inner solar system. At 3 astronomical units from the Sun, the outer edge of the habitable zone, roughly where the asteroid belt ends, the black hole's gravitational influence on Earth begins to be measurable. Earth feels a pull from the black hole that is, at this distance, about 1% of the Sun's pull. That's small, but it's not zero, and it's growing as the black hole approaches. At 1 astronomical unit from the Sun, if the black hole passes that close, the gravitational pull on Earth from the black hole equals or exceeds the Sun's pull. For a period of days to weeks, Earth is being pulled by 2 massive gravitational sources simultaneously, the Sun and the black hole. Its orbit is no longer a simple ellipse. It becomes a complex three-body trajectory: Sun, black hole, Earth. And three-body trajectories are, in general, chaotic and unpredictable. The outcome depends exquisitely on Earth's position in its orbit at the moment of closest approach. If Earth is on the far side of the Sun, 6 months away from the black hole's closest point, the perturbation is significant but survivable. Earth's orbit becomes somewhat more eccentric, perhaps shifting its distance from the Sun by 10 or 20% over the course of a year. Climate disruption follows, but the planet remains bound to the Sun. If Earth is on the near side, on the same side as the black hole, the perturbation can be catastrophic. Earth is accelerated by the black hole's gravity, gaining velocity that may exceed its escape velocity from the Sun. In this scenario, Earth leaves the solar system. There's a third possibility that is arguably the most dramatic. The black hole passes close enough to Earth that tidal forces become relevant. Tidal forces are differential gravitational forces, the difference in gravitational pull between the near side and far side of an object. For a 10 solar mass black hole at a distance of, say, 0.1 astronomical unit from Earth, about 15 million kilometers, roughly 40 times the Earth-Moon distance, the tidal force across Earth's diameter would be significant, but not catastrophic. Earth would experience enhanced tidal bulging, potentially triggering increased seismic and volcanic activity, but it would remain structurally intact. But if the black hole passes much closer, within, say, 1 million kilometers, a few times the Earth-Moon distance, the tidal forces become extraordinary. At a distance of 100,000 kilometers from a 10 solar mass black hole, the tidal force across Earth's diameter would exceed Earth's own self-gravity. This is the Roche limit, the distance within which a body held together by gravity is torn apart by tidal forces. Earth would not survive passage within the Roche limit of a 10 solar mass black hole. It would be tidally disrupted, stretched, deformed, and ultimately torn into a stream of debris orbiting the black hole. The Moon would suffer the same fate, likely before Earth, given its weaker self-gravity. The resulting debris stream would form a temporary accretion structure around the black hole, a brief, bright flare of material falling inward, before the black hole continued on its way, leaving behind a cloud of rocky debris where a planet used to be. This extreme scenario, tidal disruption, requires a very close passage and is correspondingly unlikely. The probability that a rogue black hole passing through the solar system would come within 1 million kilometers of Earth specifically is vanishingly small, given the vast volumes of space involved. But it's physically possible, and the physics is well understood. Tidal disruption events involving stars being torn apart by supermassive black holes have been observed in other galaxies, and the same principles apply at smaller scales. Now, let's step back from the extremes and consider a more moderate scenario, one that is, in some ways, more instructive because it's more likely. Suppose the black hole passes through the solar system at a distance of 2 to 3 astronomical units from the Sun, through the asteroid belt region, and doesn't directly approach any planet closer than about 1 astronomical unit. What happens? Jupiter and Saturn are significantly perturbed. Their orbits become more eccentric. Jupiter may or may not be ejected. It depends on the precise geometry. The asteroid belt is disrupted. The Kuiper belt and Oort cloud are destabilized. The inner planets, Earth included, receive a modest direct perturbation, but nothing immediately catastrophic. This sounds survivable. And in the short term, years to decades, it is. Earth's orbit changes slightly. Seasons shift. Climate changes, but within ranges that, while disruptive, are not civilization ending. Humans adapt. They've survived ice ages and warm periods before. But here's where the false sense of security dissolves. Because the moderate scenario isn't a stable endpoint. It's the beginning of a long, slow unraveling. Jupiter's new, more eccentric orbit changes the resonance structure of the asteroid belt. Over the next 10,000 to 100,000 years, the impact rate in the inner solar system increases significantly. Earth experiences more frequent asteroid strikes, not all of them large, but some of them very large. Jupiter's changed orbit also alters the orbital evolution of Mars. Over the next million years, Mars's eccentricity increases. Mars begins to cross Earth's orbital path. Probability of a Mars-Earth collision or near miss rises from essentially zero to a meaningful percentage. Saturn, perturbed by both the black hole and Jupiter's new orbit, becomes dynamically coupled to Uranus in a new and unpredictable way. The outer solar system enters a period of orbital instability that may last tens of millions of years. And Earth, sitting in its slightly altered orbit, experiences all of these cascading effects, not as a single catastrophe, but as a slow, inexorable degradation of the conditions that made complex life possible. The climate becomes more variable as orbital eccentricity changes. The impact rate increases. The long-term stability of the orbit itself is no longer guaranteed. The solar system doesn't die, it transforms. And the transformation is, from a human perspective, indistinguishable from death. But there's an even more subtle and philosophically rich version of this transformation that deserves extended attention. What happens if the rogue black hole's passage doesn't eject or destroy Earth, but instead shifts it, gently, inexorably, into a different orbit? Not a wildly eccentric orbit, not an ejection trajectory, just a different orbit, a few percent closer to the Sun, or a few percent farther away. This is the quiet apocalypse, the one that doesn't look like a disaster at first. A shift of 5% closer to the Sun would increase Earth's average surface temperature by approximately 10 degrees Celsius. That's roughly equivalent to the most extreme projections for anthropogenic climate change by the end of the 22nd century. It would melt the ice caps, raise sea levels by tens of meters, render equatorial regions uninhabitable, and fundamentally reorganize global weather patterns. But Earth would still be habitable, barely in some regions. Life would persist. It would be a profoundly diminished Earth, but not a dead one. A shift of 5% farther from the Sun would decrease Earth's average surface temperature by approximately 10 degrees Celsius. That would trigger a global ice age, not the cyclical ice ages caused by Milankovitch cycles, which involve changes of just a few degrees, but a deep, sustained freeze. Ice sheets would advance to the tropics. The hydrological cycle would slow dramatically. Agriculture as we know it would become impossible across most of the planet. A shift of 10% in either direction would be correspondingly more extreme. 10% closer might push Earth past the inner edge of the habitable zone, initiating a runaway greenhouse effect, the same process that turned Venus into a hellscape of 900 degrees surface temperatures and crushing atmospheric pressure. 10% farther might push Earth past the outer edge, causing a snowball Earth scenario from which recovery might not be possible. And here's the profound subtlety. We might not immediately know the orbit had changed. Orbital changes from a distant gravitational perturbation would be gradual from a human timescale perspective. The new orbit would be established over the course of months to years, and the climatic effects would unfold over decades to centuries. The first signs would be subtle, slightly longer or shorter years, slight changes in the dates of equinoxes and solstices, anomalies in precision astronomical measurements. Then the climate would begin to shift, warming or cooling, depending on the direction of the orbital change, and it might take years for the connection between the astronomical event and the climatic shift to be established with certainty. Imagine a world where astronomers announced that a rogue black hole had passed through the solar system and exited safely, with Earth apparently unscathed. Relief, celebration. The crisis averted, and then, over the following decades, the oceans begin to warm, or cool, and the connection is made, slowly, painfully. Earth's orbit was changed, not dramatically, not catastrophically, but enough to end the world as we knew it, in slow motion, with no possibility of reversal. This is the scenario that haunts the models. Not the dramatic explosion, not the tidal disruption, not the ejection into interstellar space. Those are violent and definitive. The quiet shift, the few percent change in orbital radius, is the outcome that is most probable, most insidious, and most human in its tragic structure. Because it's the outcome where we survive just enough to understand what we've lost. Let's shift our attention now to another scenario, one that is dramatic in a completely different way. What happens if Earth is ejected from the solar system entirely? This scenario has been modeled extensively, not just in the context of rogue black holes, but in the broader study of planetary ejection, a phenomenon that is now understood to be common in the universe. Most planetary systems go through periods of dynamical instability during their early evolution, and many planets are ejected as a result. Current estimates suggest there may be more rogue planets in the Milky Way than there are stars, perhaps trillions of worlds drifting through the galaxy, unbound to any star. If Earth were ejected from the solar system, the immediate consequence would be the loss of solar radiation. Without the sun, Earth's surface temperature would plummet. Within weeks, the surface would cool to below -100 degrees Celsius. Within months, the atmosphere would begin to condense. First the water vapor, then the carbon dioxide, and eventually, over decades, even the nitrogen and oxygen would liquefy and freeze, forming a thin shell of frozen air over the surface. The oceans would freeze over in a matter of weeks, starting at the surface. The ice would thicken over years, eventually reaching several kilometers in depth. All photosynthetic life would die quickly. All complex surface life would follow. The only survivors would be organisms that don't depend on the sun. Organisms living deep underground or at the bottom of the oceans, sustained by geothermal energy. And here's the remarkable thing. There would be survivors. Earth's internal heat, generated by radioactive decay in the mantle and residual heat from the planet's formation, would continue for billions of years, regardless of whether the sun was present. The total heat flow from Earth's interior is about 44 terawatts, a relatively small amount compared to the 174 petawatts Earth receives from the sun, but it's not zero. At the bottom of the frozen oceans, above the rocky seafloor, there would be liquid water, kept liquid by the pressure of the ice above and the heat from below. Hydrothermal vents would continue to operate, pumping hot, mineral-rich water into the deep ocean, supporting the same kind of chemosynthetic ecosystems that thrive at Earth's mid-ocean ridges today. These ecosystems, colonies of tube worms, microbial mats, strange shrimp and crabs, don't need sunlight. They derive their energy from chemical reactions, ultimately powered by Earth's internal heat. And they would persist, potentially for billions of years, on a rogue Earth drifting through interstellar space. A frozen, airless, lifeless surface, utterly hostile to anything we would recognize. And beneath it, in the dark, a thin envelope of warm water harboring the last remnants of terrestrial life. There's something extraordinarily poignant about that image. A world that once teemed with life, forests, oceans, civilizations, reduced to a handful of microbial communities, clustered around volcanic vents under kilometers of ice, on a planet that would never see a sunrise again. Life persisting, stubbornly, pointlessly, beautifully, in the dark. But would it truly be pointless? The deep ocean ecosystems on a rogue Earth would evolve. They would diversify. Over billions of years, they might give rise to complex organisms adapted to conditions that are utterly alien to anything on the surface world. Evolution doesn't require sunlight. It requires energy, replication, variation, and selection. All of those conditions would be met. And here's where we need to pause and reflect on what this scenario means. Not for physics, not for astronomy, but for us. For how we think about what makes a world a home. What is home? Is it a particular temperature range, a particular atmospheric composition, a particular brightness of sky? Or is it something more fundamental, a place where the conditions for complexity are met, where energy flows through systems of sufficient richness to sustain organization, replication, and change? If home is the latter, then a rogue Earth, dark, frozen, silent on the outside, is still a home, a diminished one, a tragic one, but a home nonetheless. And this connects to a broader truth about the universe that the rogue black hole scenario illuminates with particular clarity. The conditions we take for granted, a stable star, a stable orbit, a stable planetary system, are not guaranteed. They are contingent. They are the product of a specific history of gravitational interactions that happened to produce a stable outcome. A different history would have produced a different outcome. And a single intrusion, a single rogue black hole passing through once, never to return, could rewrite that history in a matter of months. We live in a universe where the things we depend on most, stability, predictability, continuity, are the most fragile. There is a historical parallel that illuminates this truth in a way that pure physics cannot. In the early 15th century, the Polynesian navigators of the Pacific Ocean had developed a civilization built on extraordinarily precise knowledge of the natural world. They could read the stars, the currents, the patterns of waves reflecting off distant islands, the flight paths of birds, the colors of clouds at dawn. They had colonized every habitable island in the Pacific, from Hawaii to New Zealand, from Easter Island to Samoa, using canoes and celestial navigation, covering distances that European sailors wouldn't match for centuries. Their civilization depended on stability. The stars had to be in the right places. The currents had to flow in predictable patterns. The trade winds had to blow from predictable directions at predictable times. And for centuries, they did. The Pacific was, if not unchanging, then predictably changing, varying within a range that navigators could anticipate and accommodate. But the Pacific is not actually stable. It is subject to massive aperiodic disruptions, El Niño events, volcanic eruptions, tsunamis, and longer-term climatic shifts that alter wind patterns, current flows, and island habitability. And when these disruptions occurred, the consequences for Polynesian civilizations could be severe. Islands that had been lush became arid. Fishing grounds that had been reliable became barren. Navigation routes that had been safe became treacherous. The Polynesians adapted. They were extraordinarily resilient, but they could not control the forces that shaped their environment. They could only respond to them, and sometimes, for some communities, the disruptions were too great to overcome. Islands were abandoned, populations declined, knowledge was lost. The parallel to our situation in the solar system is not exact, but it is suggestive. We, like the Polynesians, have built a civilization that depends on the stability of our environment, an environment we do not control and cannot protect from external disruption. The solar system's gravitational architecture is our Pacific Ocean. Its stability is the foundation of everything: our climate, our seasons, our position in the habitable zone, our protection from impacts. And that stability is not guaranteed. It is contingent on the absence of disruption. The Polynesians didn't know when the next El Niño would come. We don't know when or if the next gravitational intruder will arrive. But the physics tells us that the possibility exists, that the consequences would be severe, and that our ability to prevent or mitigate the event is, with current technology, essentially zero. This isn't cause for despair. The Polynesians weren't paralyzed by the knowledge that their ocean was unpredictable. They responded by building more resilient ships, developing more sophisticated navigation techniques, and maintaining social networks that allowed for mutual aid during crises. They adapted to uncertainty by becoming better at living with it. And perhaps that's the lesson for us as well. Not that we should fear the rogue black hole. The probability remains vanishingly small on any human timescale. But that we should recognize the fragility of the conditions we take for granted and invest in the resilience to survive disruptions we cannot predict. But let's return to physics, because there's one more aspect of the rogue black hole scenario that deserves extended treatment, and it's the one that most people overlook: the effect on the sun's future. Our sun is a middle-aged star. It's about 4.5 billion years old, with roughly 5 billion years of hydrogen fusion remaining before it exhausts its core fuel, swells into a red giant, and ultimately sheds its outer layers to become a white dwarf. This timeline, 5 billion years of remaining main sequence life, is well established and, barring external interference, extremely reliable. But a rogue black hole encounter could alter it. Not by physically disrupting the sun's fusion process. The sun is too massive and the black hole too swift for that. But by changing the sun's environment, specifically if the black hole's passage scatters a significant amount of material, asteroids, comets, debris, into the inner solar system, some of that material will fall into the sun. The sun already absorbs material continuously. Solar wind particles reflected back, cometary debris, interplanetary dust, but the rate is small. A major disruption of the asteroid belt or Kuiper belt could increase the infall rate dramatically, at least temporarily. More significantly, if the black hole's passage disrupts the dynamics of the outer solar system enough to send a large number of comets inward, the sun's immediate environment changes. More material in the inner solar system means more zodiacal dust, more cometary debris, and potentially more interactions between infalling material and the solar wind. The effects on the sun itself would be minimal. The sun is enormously more massive than the total mass of all the comets in the Oort Cloud. But the effects on conditions at Earth's distance could be notable. Increased dust in the inner solar system scatters and absorbs sunlight, potentially cooling the inner planets slightly. This is a minor effect compared to the orbital changes we've discussed, but it adds to the overall picture of a disrupted, destabilized system. There's a more exotic possibility as well. If the rogue black hole captures the Sun into a binary or hierarchical orbit, not ejecting it, but binding to it gravitationally, the long-term evolution of the Sun changes fundamentally. A Sun in a wide binary orbit with a 10 solar mass black hole would experience periodic gravitational perturbations that could, over millions of years, destabilize any remaining planetary orbits. The black hole would orbit the Sun, or rather, both would orbit their common center of mass, with a period that depends on the separation distance. At a separation of 100 astronomical units, the orbital period would be roughly 1,000 years. At 1,000 astronomical units, roughly 100,000 years. A binary companion of 10 solar masses at 100 astronomical units would exert a tidal influence on the planetary orbits that is, by itself, manageable, comparable to the influence of a very massive planet at that distance. But the companion is 10 solar masses, not 10 Jupiter masses, and its influence would be profoundly felt by the outer planets. Neptune, Uranus, and any Kuiper Belt objects in wide orbits would be strongly perturbed. The entire structure of the outer solar system would need to reorganize around the new gravitational reality. And here's the thing. This scenario, the Sun acquiring a black hole companion, is not as unlikely as you might think, given that the black hole is already in the solar system's gravitational influence. Capture requires the black hole to lose enough energy during its passage to become bound to the Sun. Energy loss can occur through gravitational interaction with multiple bodies, a process called dynamical friction, or through complex multi-body gravitational interactions, though a planet like Jupiter would have a negligible effect on the black hole's kinetic energy. The probability of capture is lower than the probability of a flyby, but it's not zero, especially for slower-moving intruders. If the black hole is captured, the solar system acquires a permanent new member, a dark, invisible companion orbiting the Sun, or rather, the Sun orbiting a dark, invisible master. The philosophical implications are worth sitting with. Our star, which has been the unchallenged gravitational center of our system for 4.5 billion years, would become the junior partner in a gravitational marriage. The planets, to the extent they survived the encounter, would need to find new stable orbits in a binary system dominated by an object they could never see. We've been discussing stellar mass black holes, objects of 5 to 50 solar masses. But there's another class of black hole that, while far less likely to wander into our solar system, is worth considering because it illustrates the extremes of physics. Intermediate mass black holes. Intermediate mass black holes, IMBHS, are objects with masses ranging from about 100 to 100,000 solar masses. They occupy the gap between stellar mass black holes, which form from individual star deaths, and supermassive black holes, which sit at the centers of galaxies and weigh millions to billions of solar masses. IMBHS are thought to form through various channels, the merger of multiple stellar mass black holes in dense stellar environments, the direct collapse of very massive primordial gas clouds, or the runaway accumulation of mass in the cores of globular clusters. Evidence for IMBHs is growing, but still somewhat sparse. Several candidates have been identified in the cores of globular clusters and in ultra-luminous X-ray sources, but definitive confirmation remains elusive for most. Some may have been ejected from their host clusters through gravitational interactions and could, in principle, be wandering through the galaxy as rogue objects. If an intermediate mass black hole of, say, 1,000 solar masses were to enter our solar system, the consequences would be qualitatively different from the stellar mass scenario. The gravitational influence would be overwhelming. every planet would be catastrophically perturbed. The Sun itself would be violently deflected from its current trajectory, possibly captured into a tight orbit around the IMBH. The planets would be scattered in all directions, most of them ejected from the system entirely. The encounter would not so much destabilize the solar system as disassemble it, reducing it from an organized system of orbiting bodies to a dispersed cloud of unbound objects. The timescale would be correspondingly shorter. 1,000 solar mass black hole passing through at 30 kilometers per second would complete its transit of the inner solar system in roughly 1 to 2 years, depending on its exact trajectory, speed, and the gravitational perturbations would be so severe that orbital changes would be apparent within weeks. There would be no slow cascade, no million-year unraveling. It would be a demolition. But we should be careful not to conflate the dramatic with the likely. Intermediate mass black holes are extraordinarily rare compared to stellar mass black holes. The probability of one passing through the solar system is far lower than the already vanishingly small probability of a stellar mass encounter. We consider it here not because it's a realistic threat, but because it illuminates physics at a different scale, and because it helps us appreciate that the stellar mass scenario, devastating as it is, represents a relatively restrained version of what gravitational intrusion can do. Now let's talk about one of the most fascinating and counterintuitive aspects of this entire topic. What happens to the moons? We've been focused on the planets, their orbits, their fates, their long-term stability. But every major planet in the solar system has moons, and the moons have their own stories in this scenario. Consider Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto. These are planet-sized worlds in their own right. Ganymede is larger than Mercury. Europa is thought to harbor a subsurface ocean with more liquid water than all of Earth's oceans combined. These moons orbit Jupiter in a gravitationally bound system, a miniature solar system within the solar system, and their stability depends on Jupiter being stable. If Jupiter's orbit is significantly altered by the rogue black hole, its moons go with it. The moons are tightly bound to Jupiter, and the perturbation to Jupiter's orbit around the Sun doesn't directly affect their orbits around Jupiter. They would continue orbiting Jupiter on its new trajectory, whether that trajectory is a more eccentric orbit around the Sun, an ejection into interstellar space, or a capture into a new configuration. But there's a subtlety. If the black hole passes close to Jupiter, within a few tenths of an astronomical unit, the tidal forces from the black hole could directly perturb the moon's orbits around Jupiter. The Hill sphere of Jupiter, the region within which its gravity dominates over the Sun's, has a radius of about 0.35 astronomical units. If the black hole passes within this radius, it can strip moons from Jupiter, capturing them into its own orbit, or flinging them into independent orbits around the Sun. Europa, stripped from Jupiter and flung into an independent orbit around the Sun, would be an extraordinary object. Its ice shell, currently maintained by tidal heating from Jupiter, would slowly freeze solid without that energy source. Its subsurface ocean would gradually crystallize from the top down, though the process would take millions of years due to the immense volume of water involved. During that long freeze, any life in Europa's ocean would face a slowly closing window of habitability, a drawn-out extinction as the last pockets of liquid water solidified. Alternatively, if Europa were captured by the rogue black hole and remained in a close orbit, the tidal heating from the black hole could potentially maintain or even enhance its subsurface ocean. This is speculative, but the physics is sound. Tidal heating depends on the eccentricity of the orbit and the mass of the central body, and a 10 solar mass black hole could generate significant tidal heating in a close orbiting moon. The irony would be extraordinary. The very object that destroyed the solar system's stability could become the life-sustaining patron of a tiny ocean world, providing warmth through gravity alone. Saturn's moons present similar scenarios, with the added complication of Saturn's rings. The rings, composed of trillions of particles of ice and rock, ranging in size from micrometers to meters, are dynamically delicate structures maintained by the gravitational influence of Saturn and its shepherd moons. A significant perturbation to Saturn's orbit, or the stripping away of shepherd moons, would destabilize the rings. Over thousands to millions of years, the rings would dissipate, particles spiraling into Saturn, flying off into independent orbits, or being swept up by the remaining moons. Saturn, without its rings, would be a diminished world, stripped of its most iconic feature by an invisible assailant. Titan, Saturn's largest moon, and the only moon in the solar system with a substantial atmosphere, presents a particularly interesting case. Titan's atmosphere, primarily nitrogen, with methane as a secondary component, is sustained by a complex balance of outgassing from the interior, photolysis in the upper atmosphere, and surface chemistry involving methane lakes and rivers. If Titan was stripped from Saturn and ejected as a rogue moon, or captured into a new orbit around the Sun, its atmosphere would persist for some time. It's too massive to lose quickly, but its chemistry would change radically. Without the solar ultraviolet radiation that drives the photolysis of methane, the atmospheric haze production that gives Titan its distinctive orange appearance would slow and eventually cease. Titan's atmosphere would gradually clear, revealing its surface of water ice, hydrocarbon dunes, and methane seas. A Titan without Saturn, drifting alone, would slowly lose its atmospheric methane as the reservoirs depleted without resupply. Over millions of years, its atmosphere would thin and simplify. The rich, organic chemistry that makes Titan one of the most intriguing worlds in the solar system would wind down, like a complex chemical reaction running out of reagents. The moons, in many ways, tell a more poignant story than the planets. The planets are massive enough to survive, if altered, in most scenarios. The moons, smaller, more delicately bound, more dependent on the specific gravitational environment they inhabit, are the first casualties. They are the canaries in the gravitational coal mine. Let's address another dimension of this scenario that is rarely discussed: the effect on the heliosphere. The heliosphere is the vast bubble of charged particles, the solar wind, that the Sun blows outward into interstellar space. It extends to roughly 100 to 150 astronomical units from the Sun, where the solar wind's pressure is balanced by the pressure of the interstellar medium. The heliosphere shields the solar system from a significant fraction of galactic cosmic rays, high-energy particles from distant supernovae, and other energetic processes that would otherwise bombard the planets continuously. A rogue black hole passing through the solar system would transit through the heliosphere, and its gravitational influence on the charged particles of the solar wind would be negligible. The particles are too light and too fast to be significantly deflected by the black hole's gravity. But the black hole's effect on the Sun, the subtle tidal disturbances, the potential displacement from its current trajectory, could alter the solar wind itself. A Sun that has been gravitationally jostled might produce an uneven or disrupted solar wind for a period of time, potentially creating temporary gaps or weaknesses in the heliosphere. This is a relatively minor effect compared to the orbital disruptions we've been discussing. But it's worth noting because the heliosphere's protective role is not widely appreciated. Without it, the cosmic ray flux at Earth's surface would increase by a factor of 2 to 5, depending on the energy range considered. This would have biological consequences: increased mutation rates, increased cancer risk, increased atmospheric ionization, though the effects would be far less dramatic than the orbital and climatic disruptions. More significantly, if the Sun is displaced from its current galactic orbit by the velocity kick from the black hole encounter, the heliosphere may encounter regions of the galaxy with higher or lower interstellar medium density. A denser interstellar medium compresses the heliosphere, shrinking its protective boundary and allowing more cosmic rays to reach the inner solar system. This effect has been studied in the context of the Sun's passage through galactic spiral arms, which are regions of higher gas density. The consensus is that passage through a dense molecular cloud could compress the heliosphere dramatically, possibly to within the orbit of Earth, exposing the planet to significantly elevated cosmic ray levels for hundreds of thousands of years. A sun displaced into a new galactic orbit by a black hole encounter might, over the following millions of years, pass through regions of the galaxy it would never have otherwise visited. Regions with different stellar densities, different supernova rates, different molecular cloud concentrations. The long-term consequences of this changed galactic trajectory are essentially unknowable, because they depend on the specific environment the Sun encounters. But the principle is clear. Even after the black hole is long gone, its influence persists through the altered galactic orbit of the Sun. Now let's talk about something that bridges the gap between physics and meaning. Let's talk about time. The most psychologically challenging aspect of the rogue black hole scenario is the timescale over which the consequences unfold. We've discussed immediate effects, orbital changes, tidal forces, potential ejection that occur over months to years. We've discussed medium-term effects, asteroid bombardment, climatic disruption, inner planet instability that occur over thousands to millions of years. And we've discussed long-term effects, galactic orbit changes, Oort Cloud perturbation, comet showers that unfold over tens of millions of years. No human being can experience these timescales. We live for decades if we're lucky for a century. Even our civilizations, at their most enduring, last for millennia, a blink compared to the timescales of orbital dynamics. And this creates a profound disconnect between the reality of the threat and our ability to process it emotionally or respond to it practically. Consider the moderate scenario again. The black hole passes through the outer solar system, perturbs Jupiter, and then leaves. The immediate effects are minor. A slight change in Jupiter's brightness and position that only astronomers would notice. Earth is barely affected directly. Life goes on. But the cascade has begun. Jupiter's altered orbit slowly destabilizes the asteroid belt. Over the next 100,000 years, the impact rate on Earth increases. Major impacts, events capable of regional or global devastation, occur perhaps once every 10,000 years instead of once every 100 million years. Civilizations rise and fall against this backdrop of increasing bombardment. They may not connect the impacts to the long-ago black hole encounter. They may not even know the encounter occurred. They simply live in a world where the sky falls more often, where mass extinctions are more frequent, where the window of stability within which complex civilizations can develop is shorter. And over millions of years, the orbits of the inner planets drift. Mars approaches Earth's orbit. Mercury is lost. The Earth's own orbit becomes gradually more eccentric, its climate more extreme, its seasons more violent. Life adapts, but the trajectory is toward instability. The solar system is dying, not with a bang, but with a slow, measured deterioration that no single generation would notice. This is the temporal dimension of the tragedy. The black hole doesn't kill the solar system. It wounds it, and the wound never heals. It festers slowly across timescales that no mind can encompass. Here's a question that has occupied theoretical astrophysicists, and that has no definitive answer. Has this already happened? Could a rogue black hole, or some other massive compact object, have passed through the solar system in the distant past, leaving behind perturbations that we see today, but attribute to other causes? The evidence is ambiguous. The solar system bears several features that are difficult to explain with simple models of formation and evolution. The unusual tilt of Uranus's rotational axis, nearly 90 degrees from vertical, making it roll along its orbit like a ball, is typically explained by a giant impact during the planet's formation. But a gravitational perturbation from a passing massive object could also, in principle, produce a significant axial tilt through tidal interactions. The existence of the late heavy bombardment, a hypothesized period of intense asteroid and comet impacts approximately 4 billion years ago, is usually attributed to the migration of the giant planets, specifically the model known as the Nice model, in which Jupiter and Saturn cross a mutual orbital resonance and destabilize the outer solar system. But an external gravitational perturbation, a passing star, a rogue black hole, could also have triggered a similar reorganization. The detached Kuiper belt objects, bodies like Sedna, which orbits the Sun at distances ranging from 76 to nearly 1,000 astronomical units, far beyond Neptune's gravitational influence, are difficult to explain without invoking some kind of external gravitational perturbation. The leading hypotheses include a passing star in the Sun's early life, gravitational influences from the Sun's birth cluster, or the existence of an undiscovered distant planet, the so-called Planet 9 hypothesis. But a rogue compact object passing through the outer solar system millions of years ago could also have placed these objects on their current orbits. None of these lines of evidence constitute proof of a past rogue black hole encounter. Each has alternative explanations that are more conventional and generally better supported. But they illustrate the principle that a past encounter would not leave an obvious signature. No crater, no debris field, no smoking gun. It would leave only dynamical anomalies, orbits that are slightly wrong, objects in places they shouldn't be, a subtle architecture of perturbation overlaid on the solar system's formation history. We might never know if it's happened before. The evidence may be too subtle and too old to disentangle from the many other gravitational influences the solar system has experienced over 4.5 billion years. And that uncertainty is, in its own way, profound. We don't know the complete history of the gravitational forces that shaped our home. We see the present configuration, and we assume it's the product of a smooth, uninterrupted evolution from the primordial solar nebula. But that assumption may be wrong. The solar system may have been disturbed, subtly, profoundly, invisibly, by forces that passed through long ago and left no trace except a slight rearrangement of the orbital furniture. We live in what might be the aftermath of a cosmic event we can never confirm, and we call it home. Now let's address a question that often arises in this context, and that has a surprising answer. Could we survive a rogue black hole encounter? Not humanity in the abstract, not life on Earth in the abstract, but a technological civilization, our technological civilization specifically. given decades of warning and the full resources of human technology, could we do anything to protect ourselves? The answer depends entirely on the scenario. In the extreme cases, the black hole passing through the inner solar system, direct tidal disruption, ejection of Earth, the answer is definitively no technology we possess or can reasonably envision would allow us to move a planet, resist tidal forces from a 10 solar mass object, or survive the loss of the Sun. These scenarios are, within the framework of currently known physics, unsurvivable for surface civilizations. But the moderate scenarios, the ones involving slow cascading destabilization rather than immediate destruction, offer more room for adaptation. If the black hole's passage leaves Earth in a slightly altered orbit, the resulting climate change would be severe, but potentially manageable on civilizational timescales. Humanity has demonstrated the ability to adapt to dramatic environmental changes, and a technological civilization with decades of warning could prepare. Building underground habitats, developing new agricultural techniques, engineering atmospheric interventions to compensate for changed solar radiation levels. The increased impact risk from a destabilized asteroid belt is, in some ways, the most tractable threat. We are already developing asteroid deflection technology. NASA's DART mission successfully demonstrated kinetic impactor deflection in 2022. And a civilization with strong motivation and centuries of lead time could potentially develop the capacity to detect and deflect most threatening impactors before they reached Earth. This wouldn't eliminate the risk, but it could reduce it to manageable levels. The long-term orbital instability, the million-year timescale drift of Mars, the gradual increase in Earth's eccentricity, is beyond any foreseeable technological mitigation. We cannot adjust the orbits of planets, but 1,000,000 years is a long time, and a civilization that survived the first few centuries of adjustment might develop technologies that are currently unimaginable to us. To restrict the analysis to currently known technology is to underestimate human ingenuity, a mistake that history has consistently punished. So the answer is maybe. In some scenarios, with enough warning and enough luck, technological civilization could survive, diminished, transformed, but alive. In other scenarios, survival is not plausible. And in all scenarios, the solar system that emerges from the encounter would be a fundamentally different place than the one that went in. This brings us to a question that isn't scientific at all, but that science compels us to ask. What does it mean to live in a universe where the conditions for our existence are contingent, where the stability we depend on is not a permanent feature of reality, but a temporary condition, vulnerable to disruption by forces beyond our control or comprehension? What does it mean that the same gravitational force that holds us in orbit, that keeps our oceans liquid and our atmosphere bound, that allows seasons and tides and the slow pulse of life, that this same force could, in a different configuration, strip all of it away? What does it mean that the boundary between a habitable world and a frozen rogue planet is nothing more than a number, a distance, an eccentricity, a mass ratio, and that number can be changed by a passing stranger that doesn't even know we're here? What kind of universe allows for that? And what kind of beings are we that we can know this, can calculate it, model it, narrate it, and still go on living as if the ground beneath us is permanent? These are not questions that physics can answer. Physics can tell us what the universe does. It cannot tell us what the universe means. But the act of asking, the act of looking up at a sky full of stars and understanding, really understanding, that the order we see is fragile, is itself meaningful. It is the act that makes us human. The Polynesians, again, are instructive here. They knew the ocean was dangerous. They knew that storms could come without warning, that currents could change, that islands could disappear beneath rising seas. They did not let this knowledge paralyze them. They used it to navigate more skillfully, to build more seaworthy vessels, to cultivate a culture of awareness and adaptation that sustained them for centuries across the vastness of the Pacific. We too can use the knowledge of cosmic fragility, not as cause for despair, but as motivation for vigilance, for curiosity, for the expansion of our capabilities beyond the boundaries of a single planet. The rogue black hole scenario, however improbable, is a reminder that Earth is not a fortress. It is a ship, and like any ship, its safety depends not just on the integrity of its hull, but on the awareness and skill of its crew. Apollo 8, in December of 1968, carried 3 human beings around the moon and back. During the mission, astronaut Bill Anders took a photograph that came to be known as Earthrise, a picture of the Earth, small and blue and achingly fragile, rising above the barren lunar horizon. It became one of the most reproduced photographs in history, and it is credited with sparking a revolution in environmental awareness. What made the photograph so powerful was not the beauty of Earth, though it was beautiful. It was the context. The moon was dead, space was black, and Earth, in the photograph, was visibly alone. A small, bright, delicate world floating in an ocean of emptiness. There was nothing else. No backup, no second planet waiting in the wings. Just Earth, in all its complexity and fragility, against the void. The rogue black hole scenario is, in a sense, the narrative version of that photograph. It shows us our world not as we experience it, solid, permanent, inevitable, but as it actually is, a temporary arrangement of matter and energy, held in place by forces that are powerful but not inviolable, in a universe that is vast, dynamic, and profoundly indifferent to our survival. That indifference is not cruelty. The universe doesn't wish us harm. It doesn't wish us anything. It simply is, a place of gravity and light and time, where matter organizes itself into patterns of extraordinary beauty, and then, eventually, reorganizes into something else. We are one such pattern. The solar system is another, and both are subject to the same laws, the same contingencies, the same fragile dependence on conditions that could change. Let's step back and bring this together. We started with a misconception, the idea that a black hole is a cosmic vacuum cleaner, a hungry predator that devours everything in its path. We demolished that misconception with physics. A black hole of a given mass exerts no more gravitational pull than any other object of the same mass at the same distance. Black holes are not special in their gravity. They are special in their density, in their event horizons, in the extreme warping of space-time at close range. But from a distance, they are simply mass. And mass, in Newtonian mechanics, attracts other mass according to one simple, universal law. Then we explored what that law actually implies when a massive object, a rogue black hole of perhaps 10 solar masses, enters a system of delicately balanced orbits. We traced the approach from the Oort Cloud to the Kuiper Belt, to the giant planets, to the inner solar system. We examined the immediate effects: orbital perturbation, tidal forces, potential ejection or destruction of planets. We examined the medium-term effects: cascading instability, asteroid belt disruption, increased impact rates, climatic chaos. And we examined the long-term effects: the slow, irreversible unraveling of orbital stability over millions of years. We considered the fate of the moons. Europa's subsurface ocean freezing slowly in the dark, Titan's atmospheric chemistry winding down, Saturn's rings dissipating without their shepherd moons. We considered the fate of Earth in the most extreme scenarios: tidal disruption within the Roche limit, ejection into interstellar space as a frozen rogue world harboring the last remnants of life around deep-sea vents. We considered the detectability of the threat, how a solitary rogue black hole, emitting nothing, reflecting nothing, would be functionally invisible until it was already among us. We traced a fictional but physically plausible detection scenario, from the first anomalous perturbation of Neptune's orbit to the confirmed identification of a 10 solar mass intruder on an unstoppable trajectory. We considered the survivability of the threat, from the impossible extreme scenarios to the barely manageable moderate ones, and concluded that a technological civilization might, with enough warning and ingenuity, adapt to some outcomes while being utterly powerless against others. We considered the historical precedent of past disruptions, the unexplained anomalies in the solar system's current architecture that might or might not be the signatures of a long-ago gravitational encounter that left no obvious trace. And we asked what it all means, not for science, but for us, for beings who live for decades in a universe that operates on timescales of billions of years, for beings who build civilizations on a foundation of stability that could be removed by a force they can neither see nor stop. The answer, or something approaching an answer, is this: the fragility of our cosmic situation is not a reason for fear. It is a reason for attention. It is a reason for the precise kind of curiosity that drives us to study black holes, to model gravitational dynamics, to send spacecraft to the edges of the solar system, and to look up at the night sky and wonder. Because the alternative to knowing is not safe. The alternative to knowing is ignorance, and ignorance in a universe as dynamic and indifferent as ours is the most dangerous state of all. A rogue black hole will almost certainly never enter our solar system during the remaining lifetime of our sun. The probabilities are overwhelmingly in our favor. We will, in all likelihood, never face this particular challenge. But the universe is vast, and time is long, and there are trillions of rogue objects, black holes, neutron stars, rogue planets, wandering stars, drifting through the galaxy on trajectories we cannot predict. The solar system is not a sealed room. It is an open space, vulnerable to whatever passes through. And the stability we depend on is real, but not permanent. A 4.5 billion-year-old arrangement that has survived not because it is indestructible, but because, so far, nothing has come along to destroy it. So far. There's a particular kind of beauty in that, so far. It's the beauty of impermanence, the knowledge that what we have is precious precisely because it is not guaranteed. The blue of the sky, the rhythm of the seasons, the steady warmth of a yellow star 93 million miles away. None of it is eternal. All of it is the product of a specific gravitational history that could have gone differently, and that, someday, might. The Earth orbits its star tonight, as it has for 4.5 billion years, in a configuration so finely tuned that a nudge of a few % in any direction would render it uninhabitable. That orbit is held in place not by any cosmic intention, but by the same blind gravitational force that would, in different circumstances, tear it apart. And we are here, awake, aware, asking questions, in the narrow window between the formation of the solar system and whatever comes next. If this changed how you think about our place in the cosmos, then the time was well spent. Thank you sincerely for staying through the entire exploration. Wherever you are, whatever time it is, the same gravity that holds you to this planet holds the planet to its star, and the star to its galaxy, and the galaxy to its cluster. It is all one force, one law, one fragile, magnificent arrangement. And tonight, it holds